All right, and we are going live. What is up, everybody, to Data on Kubernetes Community's live stream number 136. Super stoked for today's live stream. As always, we've got an amazing speaker with a very, very cool topic, almost controversial. I don't want to use the word controversial, but it's certainly exciting. It's innovative. It's going to be fun. We're going to be looking at a very new space. I had not heard about database mesh up until I had met our speaker, Maxwell. So very stoked to hear what he's got to say about this topic. Before we get into that, all right, just want to make sure that you are up to date about things that are happening in the Data on Kubernetes community. We've got our meetup that's happening in person in London at the end of this month on June 30th. I'm going to drop the link there. So if you're in London, if you know someone who's in London, if you think you know somebody who's in London, we've already got about 60 people signed up for this in-person event. All right, we're going to have some lightning talks, panels, interviews, all kinds of goodness. A really, really cool spot in a rooftop sort of location in London. Weather should be good. It's going to be really, really nice time. So definitely check that out. Also, if you have not seen yet, all right, we have the DoK landscape, all right, which is a portal where we are featuring the technologies of the members, our wonderful sponsors in our community. Shout out to our sponsors. And you can check that out right here. All right, the DoK landscape, where you can see the different technologies that are being featured in order for end users to have an easier time when it comes to deciding which technology is going to be best for them. All right, so make sure that you check that out. That being said, all right, with no further ado, we've heard of service mesh. You may have heard of data mesh, right? We know, but database mesh was something that kind of took me by surprise. So today we have an expert on the topic, right? His name is Maxwell. He joins us from a different time zone where it's much later than it is here. It's about midnight where he is. It's about 6 p.m. where I am. If you're in the West Coast, it's around 9 a.m. So you got people literally all over the world that are watching this. Maxwell, welcome to the Data on Kubernetes community. How are you doing today?
Yeah, it's okay. I'm doing good.
Good. All right. That being said, can you tell us a little bit about yourself? If you want to start sharing your screen, you can do that and we can see your presentation.
Okay, I'd like to share my screen.
Good.
Okay. Yes.
Perfect.
Okay. So I'm going to start my talk. Hello, everyone. Thanks for your attending, and I'm so thrilled today to have this talk tonight. Yes, it's midnight in China, and I still feel the deep excitement about this meetup. So in this talk, I'd like to share the stories behind database mesh and our open source project, Pisanix, and talk about building a mesh for databases from scratch and why. Oh, okay. At the very beginning, I'm going to thank Data on Kubernetes community and thanks for your support about database mesh and this talk. And I am Maxwell. I'm from China. I'm now working as the head of a cloud department of SphereEx. SphereEx is a startup about database infrastructure in China. So you maybe hear about Apache, ShardingSphere. The founders of ShardingSphere founded this company last year. In the past, I worked as the senior developer, cloud infrastructure architect at NetStars and Ant Group, and I'm working with Kubernetes since 2015. And I'm also a Gopher and a Rustician. So, you know, writing a Go-long program and a Rust-long program is very, very different. So it makes me sometimes a little bit brain splitting about the two programming languages. And I love open source and cloud native, and I also have two cats. They often do some code review and find bugs for me. Yeah. So you can either follow me on Twitter or just send me an email about anything you want to talk to me. Okay, so let's get started. There will be 3 parts of this talk. Begin with service mesh, the mesh model, and the building with Rust and Go. At first, let's talk about service mesh. The concept of a service mesh was first proposed by the creators of Linkerd. I remember at that time around 2016. There were only a few of companies in China who adopted Kubernetes, and most of them, before they adopted Kubernetes, most of them have already had some service governance frameworks like Double. Service mesh brought us a new perspective of service governance in Kubernetes. Um, that is, the service mesh, it uses a transparent layer as a data plane through a sidecar pattern. And the proxy will hijack all the traffic from your application and receive the configuration from the control plane. The configuration including some service discovery about rate limiting, circuit breaking, access control, and certifications. So the service mesh framework provides everything about service governance for cloud native applications. The proxies of applications have built a huge mesh to the deployment of applications. So we consider, we give it a name about service mesh. Generally, I have to say service mesh is not a silver bullet, and it's clearly a product of a technology evolution. I mean, before service mesh, even before microservices, we can see some application architectures as monoliths. Monoliths wasn't any evil, but it was so appropriate at that time. I mean, we don't have businesses so complex as today, and we also don't have tons of requests, traffic need to handle. So with the growth of 3G, 4G, and any other communication technologies, our business had come to a new stage. I mean, we call it a mobile internet. So people can browse news, response instance messages, and watch short videos at any time, anywhere. This really a life on the go pattern. Like I said, from that time, monoliths can no longer support the quantity or the huge information. So we have to decouple our monolith architecture. We have the microservices. The deployment pattern and operation also have changed. So in a word, from monolith to microservices, the scale of an application deployment grows and brings more complexity to the service dependencies. A microservice governance focus on some common topics like traffic control, like observability, like security, like access control, configuration management, and high availability, failover, as so many things. But we back to service mesh around 2017. Istio announced its first release. The Istio addresses the challenges developers and operators face with a distributed or microservice architecture. Whether you are building from scratch or migrating existing application to cloud native, Istio can help. This is important. This means Istio has made service mesh on Kubernetes crystal clear, and indeed have a lot of influence on the later design of different mesh frameworks. So here comes the first question. We know that service mesh could hijack all traffic from application by the proxy. What if we put a MySQL into the service mesh? I mean, in fact, if we consider MySQL as a normal microservice node in our architecture, it has no difference with any other services. But I have to say this is not enough for MySQL. Now let's dive into the second part, the mesh model. For Istio, that it has the Istio T, Istio D, including a pilot, a Sidentil, and a Galley. It also uses NY to proxy application traffic to the upstream and downstream. So application container coexist with NY container in the same pod, sharing the same network. So with the help of IP tables, all traffic sent from the application container could be redirected to the NY proxy. And NY will decide where to route the different requests. Istio has achieved this by some customer resource definitions like virtual service, like a destination role to build a NY configuration. Many companies have adopted Istio as their first choice of service mesh, and other companies try to do some development based on Istio to fit their own use cases. So Istio is popular, but does service mesh means Istio? No, we can put many other different service mesh projects if you want to draw a landscape of service meshes, including Motion from Ant Group, App Mesh from AWS. I don't think this is a reinvent of wheels. I feel excited about the ecosystem. It means there's a very active community about service mesh, and people cares about service governance in the Kubernetes and try to find a different way to solve the problem. So this is we do thinking about something. And besides the great help of microservice governance from Istio, I think it also tells us what is a mesh pattern. Classically, the mesh pattern often have two components. The first one is a control plane, like the below in the graph is Istio D. Istio D as a controller in the control plane, so it is responsible for all the management stuff. It has no sense over the traffic itself. And another one is data plane, the upper in the graph, I mean the NY proxy. NY proxy will hijack all the traffic, like I said before, and working as a transparent proxy at the bottom of your microservice. So people want to consider Istio or NY as a part of infrastructure. Yeah. But does the mesh means a sidecar pattern? Even we always equals mesh to a sidecar pattern. No, unfortunately, the answer is no. The mesh is not a thing about the sidecar, in my opinion. Clearly, mesh is just a best practice of some technology, framework or architecture design. It's just one way we could use to solve the problem. We can also have any other solutions. Like we using double, we have to put the double application out of the Kubernetes cluster, and every application containers have register to the registry and do some service governance stuff. The important thing is the problem we care about, but not the tools, but not the framework, not the sidecar. So this graph I have copied from the QSmash official website, and it shows how QSmash work. Sidecar is not a required component in QSmash. So QSmash, we can use a daemon set named chaos daemon. So we still could make some chaos to the application deployed in that framework. Istio really cares about the traffic, and it's definitely right. Traffic management is really the core of large-scale microservices. Istio wants to solve it, make it easier, and that there's no doubt about it. But what does a mesh being used for? I mean, I have to see if it's not about traffic. We have several different meshes like open service mesh, like chaos mesh for the chaos engineering in the cloud native, and the event mesh and L mesh. They are different mesh solutions for different problems. So what about database mesh? In 2018, there was a post about database mesh published in the InfoQ China. The writer Zhang Liang is the founder of Apache Sharing Sphere, and the article is really long to read. I have do some conclusion for you. So the writer Liang proposed a model. It wants to use a sidecar for database traffic management. Imagine that it's something like put a sharding sphere proxy into a container and be injected into the port. So what's the difference between service mesh and this database mesh? Liang believes the database traffic has some domain-specific characteristics, like we do data sharding. The proxy has to know the SQL and parse into an abstract syntax tree. This cannot be simply considered the same with layer 4 traffic. Besides this, the proxy also need to support like read-write splitting, data encryption. So that's what database mesh means at that time. So let's see this picture. We compare service mesh with database mesh. They both can handle traffic. From the perspective of layer 4 traffic, it's nearly same, like service discovery, load balancing, security, and then provide some other observability like logging, monitoring, tracing, and also provide some support for the security features, access control, blacklist certification. So what will be the first different feature added to database mesh? In the past 4 years, since the database mesh concept was proposed in China, companies in China have practiced database mesh in 3 major ways. The first one is introduce the sharding sphere sidecar. The sidecar acting exactly same with the sharding sphere proxy, and it will do some data sharding, encryption, read-write splitting from a sidecar. And the second one is often adopted by large companies like BAT. They build a unified layer to manage all of their mesh things, handle application traffic and database traffic at the same time. So the configuration for application traffic and database traffic from the same control plane and using the same proxy in a sidecar in the application pod to handle the different traffic. The third one is building a distributed database with the help of a sidecar. The sidecar play a role as a handling database access and communicating with the centric transaction manager, storage manager, and log servers. So I'm so excited about all of these practice, even they are so different. But when we think about database governance, the concept, the domain itself, and I have talked to several DBAs, does database governance only cares about traffic? Is traffic everything of a database mesh? That's an important question. So if we see the previous database mesh as version 1, so how about the version 2? I mean, if we ourselves are SRE or DBAs, what do we really want to have in this database governance area? I mean, do we care about resource consumed by our databases? Do we need a pipeline or schema change? Are there some ways to make DBAs life easier, like putting MySQL PG Redis in the standard framework? And how about easy of use thing? DBAs could write customer resource definitions, but let the framework handle the rest of the work. So that is what I'm talking about database mesh. It will build an efficient and programmable database governance experience in the cloud native era. So you can check the website below and our GitHub repo to get more details. Let me explain this to you. In the database mesh version 2, it focuses on how to let the burden of developers to boost their business. I mean, it's something like the serverless concept. Let developers focus on the business logic, don't care about care about the infrastructure thing. And the second, the database mesh want to achieve a framework which includes database traffic, runtime resource, and reliability for databases in a configurable and pluggable, programmable way. In a word, the database mesh want to handle the traffic, like the load balancing, like access control, like read-write splitting, even sharding, and also want to handle the runtime resource thing. Here's an example. I mean, if your databases traffic need to be separated with your application traffic, database mesh will provide some way to help you achieve this. To eliminate the impact of different traffic, yeah. And in a configurable or pluggable or programmable way, I mean, the database mesh framework will try to make itself with a more extensible. People can write plugins, no matter it's a Lua plugin or Western plugin, to help this framework become a more strong platform. The third one is provide a standard interface for a variety of databases, no matter it's cloud native or distributed databases. In the left of this slide, I mean, the database mesh want to use the common workloads, the standard workload. For example, the TrafficStrategy to handle, no matter it's MySQL, it's PG or Redis, the traffic. All of these databases need to handle to take care of their traffic, and this is not this is vendor lock-in. No matter it's AWS or Google Cloud, the framework also works. So the database mesh proposed database-centric governance framework. We consider database as the first-class resource in the framework, and we want to build an engineer-friendly experience. Database mesh want to let developers only care about the protocol about their databases. The developers, no matter they write Go or Rust, they only have to claim a type or protocol over their database to fit their business needs. No worries about the operation characters of the database itself, and the database mesh will try to make some automation for the operation of the database in a declarative way. Write some CRDs, let the operator do the thing. Yeah, and the third one is with our open community to adopt databases from different cloud vendors, and build a framework on top of cloud native architecture without any vendor lock-in. So here's the last part, and I want to talk about how to build this with Rust and Go. The first question is why Kubernetes? Kubernetes is a de facto standard of cloud native, and we have put all of our applications running on the EKS. Kubernetes is the so-called a platform of platform. We can build our like path or container as service on top of the Kubernetes. And the pod is a basic scheduling unit, serves for different deployment patterns. And the sidecar container, it coexists with the main container in the same pod. It shares the same life cycle with the application container, and also share the network namespace and file mounts. So the service mesh use sidecar pattern to decouple business container and the proxy container. A very classical example is we set a logging collector as a sidecar into our application pod, and the collector will send the logs to the external, Kafka or Elasticsearch. The second pattern of Kubernetes is admission webhook. Kubernetes server supports extensions of webhook, and it will handle all of the requests in a Kubernetes cluster. And admission webhook, it consists of two kinds. First one is validating, and the second one is mutating for date validation and mutation respectively. So we could write some customer resource definition with the help of admission webhook. If you want to inject the sidecar into the pod without any developers know about the thing, so we can use mutating admission webhook to achieve this transparent injection. And the last one is customer resource definition. This is the core of Kubernetes, and the Kubernetes is called a platform for platform because of the CRD. Kubernetes controllers implement declarative API through the watchlist mechanism natively. So we can write our customer resource definition and put what we want to do described in the YAML manifesto, and let the controller to handle the work. So CRD works with controller. We can also call it operator pattern. And now let's get back to the database mesh design. So what does the control plane in database mesh looks like? The control plane in IS2, as I said before, it handles all the management stuff. It converts the customer resource definition from Kubernetes and to the NY configuration. So it is the same to database mesh. The control plane in database mesh will do two things now. Currently, it supports sidecar injection using the mutating admission webhook to inject the sidecar into the selected pod. This is same to the IS2 service mesh. And the second one is configuration conversion. The control plane will watch the Kubernetes API server to get the CRD and convert it to the data plane configuration, including load balancing, concurrency control, security. All of the features are based on the SQL, not just a layer 4 traffic. So we have a controller, we call it PISA controller. PISA controller is the main component of our design. And it will handle the sidecar injection and convert the configuration. And what does the data plane looks like? In database mesh, we want to handle the traffic, the runtime resource, and even some database reliability engineering thing. So we could imagine that the main feature of a data plane. The first one is SQL traffic control. We want to hijack the SQL traffic and know where to route the SQL. And the second, we could provide a fine-grained access control role according to the user and the data relationship. This may be a table level or a column level access control. And other features like circuit break reject high-risk SQL execution and observability to expose some metrics about the SQL processing procedure, like how many SQLs have been processed and how many SQLs, the latency about the SQL processing. The last one is runtime resource management. Like I said before, we want to providing a TrafficQoS with the help of some technology like eBPF. So we have the first data plane. Note, it's the first data plane. We call it PISA proxy. A PISA proxy will be the sidecar to the application pod, and it will also be injected transparently. The application will only to change their configuration about the database access information. Now, let the configuration point to the endpoint provided by the PISA proxy. This is different from the NY. NY will hijack the traffic transparently by the help of with the help of IP tables, but PISA proxy need the application to change their configuration. And another one data plane is PISA daemon. PISA daemon currently is not released and will coming soon. PISA daemon, we deploy it on the Kubernetes node as a daemon set. It will handle the runtime resource management. Currently, this is we have a demo about this feature, but it cannot be released at present. The PISA daemon, because it's close to the node and close to the operating system, they can utilize the features of a Linux kernel to accomplish some runtime resource management needs. So we compose the different three components into our project. It is Pisanix. The Pisanix is a solution of database mesh, and it is written in Go and Rust, and it is Kubernetes native. Currently speak MySQL. The main features of Pisanix is SQL-aware traffic control. SQL-aware traffic control, it's a difference with service mesh. So we have to know what the SQL really means and wrote it. And the second one, it will support the runtime resource-oriented programming to let the extensible resource control abilities. And the last one, database reliability engineering. Pisanix want to help the DRE on the Kubernetes, make DBAs life easier with the Kubernetes. So Pisanix have three components. The first one is Pisa controller. It is a required component as control plane. And the second one is Pisa proxy written in Rust. It is also a required component. The third one is Pisa daemon. It has not been released now, and it is optional. So I will explain how do we build the Pisanix. Let me demonstrate with Pisa proxy. Pisa proxy was built in Rust. We choose Rust because it is a system level language. It has really a lot of advantages in programming. Like it follows the design principle. It will provide a secure, reliable, and efficient way to write your program. And I also support multiple paradigms like object-oriented programming, functional, or producial. And it also provides a memory safe model. It can achieve memory safe through type safe like ownership, borrow, and lifecycle markup. And it uses zero cost abstraction explanation at the compiling time with generics and trait. And it also has some engineering help. It's the package management create the commands, the different style of commands, and the compiler information to help you find your design drawbacks at compiling time, and also provide a very good error and exception handling mechanism. So the whole procedure of Pisa workflow, the Pisa proxy will speak MySQL protocol. So in the application's perspective, it will consider Pisa proxy as a database and MySQL. So Pisa proxy speaks MySQL, and the application could connect to it directly. So the application will need to modify their configuration about database credential. And the Pisa proxy read handshake and data packet from the application and read the expected SQL. The SQL will be parsed to get the AST. The AST-based advanced access control want to know if this table could be read or write from this application. And the parser will also help to build like some SQL secret. After pass this access control and firewall, the SQL will be submitted to the execution. The metrics are now collected to the SQL execution, and we will choose a proper backend connection according to load balance strategy to proxy the SQL to the backend, to the real backend of the database, and send the SQL to the backend data sources and read the response, and finally write back the data response to the application. So at this time, Pisa proxy, you can see it is database middleware or database proxy, like the MySQL router. So the Pisa proxy have to support MySQL protocol. On one hand, Pisa proxy speaks the MySQL server, so it receives the TCP handshake from the application and write back the first initial handshake packet to the application. On the other hand, MySQL proxy will work as a MySQL client. Pisa proxy will work as a MySQL client. It will set up connections with the backend database resources at the startup and maintain a connection pool to the databases. And it will make up the handshake response with flags and SSL to exchange handshake information to the backend database resources. And finally, establish the connection. And Pisa proxy also need to do some SQL parser. When only we have pass the SQL, we can know the intention over the SQL. So to do more advanced features like SQL break or access control. So Pisa proxy use grammar tools to build a SQL parser according to the MySQL YCC file. And the scanning parser will read a SQL token and pass them to the Lexer and and create the STs, and receive SQL table and column information from the STs to implement the column-based fine-grained access control and even data sharding and encryption. The SQL firewall is to reject the SQL. Those are not allowed to be executed. And we also support the concurrency control based on the time and regular expression. That is, we have to set a time window to the Pisa proxy. In this time duration, the SQL statement match the regular expression will not be allowed to execute at some parallelism concurrency control. And the Pisa proxy will also provide a load balance feature. Currently, it supports basic load balances strategy. I mean, in the read-write splitting scenario, the Pisa proxy will try to send SQL to different database backend if they are all reader label. And we want to support a label-based role. People can write their role like a regular expression and some maybe label selector to spot the different or complex SQL roles to rotate to the different backend of database sources. And finally, it will become a strategy framework. Users could submit their predefined strategy and customer the role, even customer the strategy controller itself. Observability is the common between service mesh and database mesh. So we have hijacked the traffic, so we can do anything about the traffic. We can see how many SQL per asset total and how long does the SQL being processed. But currently we only support 2 metrics now. We have a plan to support more metrics like top queries by total time, top queries by the count, or SQL runtime memory. SQL runtime memory is related to the Pisa daemon. We want to describe the memory consumed in one SQL execution, while the SQL is execution. So we want to prevent sending other SQL to one proxy and make the load balance more understandable. And this is the Pisa daemon. Pisa daemon, I think it will use the Linux kernel capabilities like eBPF, extended eBPF, to provide us some mechanism to support very advanced runtime resource management. The eBPF will provide a sandbox for application running near Linux kernel, and it could be considered as secure and efficient kernel extensions. It has the 4 main use cases in observability, security, network, and tracing. So eBPF could collect a variety of metrics in the kernel and expose them. And eBPF could observe all the system calls, and with the help of package and socket management, process context tracing mechanism and achieve fine-grained security control. And eBPF also feeds the traffic package handling without leaving the kernel network context. And the eBPF is very useful for performance tuning to provide user mode process and system calls. Yeah, even implementing zero intrusion tracing capabilities like the Pisanix project. Here's an example what we want to do use the Pisa daemon and eBPF. In the graph, we have 2 applications, maybe on the same node, and we have set different priorities to the application, so it was colored in different color. Each application have their own PISA proxy to proxy their database request. The PISA proxy will execute the SQL, and according to the priority of the application, the PISA proxy will make some label or mark on the traffic. And the PISA daemon will read this mark to put the traffic, to put the TCP packets into different QoS class. The QoS class we can implement with TC in Linux, and to set different classes with different kind of maybe bandwidth. So the traffic will be routed in different QoS class to prevent their interaction. And finally, the traffic will be handled to the backend database source. This is just an example, and we have provided a demo about it. And this is I think this is important to some online and offline, I mean, large scale Kubernetes clusters. So we want to provide an extension mechanism for supporting more runtime resource management plugins. As I said, Pisanix is designed for Kubernetes, so we recommend to deploy Pisanix in Kubernetes. Here's another example of how do we use Pisanix in Kubernetes. We can see there are 3 workloads now. The first one is virtual database. The second one is TrafficStrategy, and the last one is DatabaseEndpoint. In the virtual database, we can see there are some properties like DB, like host ports, the database access credential, and it has some traffic strategy to be bound. The traffic strategy it announces the concurrency control rules, the circuit break rules, and the load balancer strategy. It's random now. And the last one, database endpoint, it refers to the real database endpoint. Maybe it's a host over AWS RDS or just a host from your MySQL. So the whole workflow of Pisanix is Pisanix works in a way of control plane and the data plane. It's the same with service mesh, and Pisanix will inject PISA proxy to the pod who is labeled with Pisanix IO /inject, and the developers need to submit the virtual database CRD, claiming they want a database to be used by their application. With the help of different controllers, they will create maybe a RDS on AWS and take the and put the information into a database endpoint. And finally, the DBA or the SRE will bind the traffic strategy to both the virtual database and the database endpoint. So that is a complete proxy chain. The PISA controller watches customer resource definition and converts to PISA proxy configs. And the PISA proxy will receive the configs and create connection to the backend databases. So you can just start your application and access maybe localhost directly. But PISA proxy, we consider not every company need to deploy it on the Kubernetes. Even to some startup or smaller company, they also need to handle the database proxy layer. So PISA proxy could be deployed in the standalone mode as a unified access layer for databases. No matter their RDS, MySQL, sharding Sphere, they could be supported with read-write traffic splitting, high availability failover, and SQL-oriented availability. So here's the last question. Why do you need a database mesh? And I want to show you the takeaways about this talk. So if you want a serverless experience over databases, you want your developers only need to care about the type of databases. So you could let your infra leader to consider Pisanix. And if you want to have all your applications and databases hosted on cloud, Pisanix could simplify that. And if you are a DBA and really want all of your databases be managed in a standard way, Pisanix comes to help. And the last thing is, if you are good at hijacking, feel free to write some plugins to boost the Pisanix. So I want to see that Pisanix community really needs your help. That's all I want to share during this talk, and I'm sorry for the poor English because it has been very long since last time.
Oh, come on! There's zero problem with the English. You covered a lot of concepts, a lot of different things that we saw there, but very, very well put together. I think we have a much better idea now about what database mesh, excuse me. And also, like you said, if people want to know more, they know what communities they need to join. They know what technologies they need to be looking at. I shared a screenshot from the beginning when you were explaining about, what database mesh is. And then I think the takeaways at the end were also very, very good. So excellent job, Maxwell. Can you stop sharing your screen really quickly?
Okay.
Cool. So we have a tradition in our community that while our speaker is talking, we have our amazing artist who's in the background, who's drawing while you're speaking. So he created an artistic depiction of the different things that were being touched on here. And as we can see, they're all connected in a mesh. So anyway, very, very good stuff. I think, it's interesting that you mentioned the article that came out in 2018. So this is a concept that has now existed for, around 4 years, but it's good to see that these things are maturing, that more people are working on them. And as you said, that there is a community where people can go to interact, to get more experience. So Maxwell, thank you very much for your time and your presentation today. If anybody has any questions, it's now almost 1 a.m. in China, so I think Maxwell needs to go to bed. But if you want to continue the conversation, please feel free to ask any questions you might have in Slack, and we would love to see these ideas continue to flow. And I hope that we will have you back for, KubeCon in October, another live stream, because this concept of database mesh, I think is very interesting, and more people will want to know about it. So anyway, Maxwell, thank you very much for your time today, and we look forward to seeing you soon. Okay?
Okay, thank you.